All right, this is AP, AB, and BC Calculus. We are doing Unit 4, Section 4, which is an intro to related rates. This section and also the next section will be on related rates, so we're going to do an introduction and sort of easier problems here and then slightly more complex problems in the next video. So related rates are generally word problems, apologizing in advance for that. In the problems, multiple quantities will be changing, hence rates, and those quantities will have an effect on each other, hence related. So, for example, if I'm inflating a spherical balloon by blowing air into it, I'm changing the volume of the balloon. The rate at which I'm blowing in the air would be dV dt, meaning the rate of change of volume, hence dV, change in V, with respect to time dt. As I do this, the side effect of this is that the radius of the balloon will also increase. This rate would be dr dt, which would be the rate of change of the radius with respect to time, and I'm slightly annoyed by the lack of the second parenthesis there, but it is what it is. So in this video, I'm going to introduce you to a method called Dredsaw, which is really just an easy way to remember the steps in order to solve related rates problems. And I'm going to walk you through applying that method in a few simple examples. Next section, we'll do the more progressively difficult examples. All right, so Dredsaw. I saw this on the internet years ago as dreads and thought, oh, hey, that's super duper clever. So definitely not my idea. And then what I noticed is that my students were frequently doing all of the steps right and then forgetting to answer the question, so I made it Dredsaw. So again, borrowed dreads from the interwebs and then just added an A on the end. So D is draw a diagram. Sometimes there's a diagram given, but if there's not, it's often helpful to visualize what's happening. R is rates, variables, and constants. You want to label those values on the diagram. Equation is E. You want to write one that relates the variables. And so just notice down here there's an asterisk. The equation is usually one you know, like Pythagorean theorem or the area of a circle or the area of a triangle or SOHCAHTOA. It's very frequently something you know. D, derive, usually with respect to time. S, substitute specific stuff. Not fun to say that a bunch of times fast. Those will be the values that are only true for a specific time. So the values that go on the diagram here are values. So picture this as like a video, right? Things are moving. There are rates. The ladder is sliding down the wall. The balloon is inflating. The substitute specific stuff is like a picture. It's a single moment in time frozen when certain values are given, right? When the ladder is a certain distance from the building or the balloon has a certain amount of air or whatever. And then lastly, answer the question with appropriate units. If there are units, sometimes there aren't. But again, a lot of my students would do all the steps right and then forget to answer the question, hence Dredsaw. So let's walk through this. A 15-foot ladder is leaning against the gym wall. Pitts pulls the base of the ladder away from the wall at a rate of 2 feet per second. At what rate is the top of the ladder sliding down the wall when the base is 9 feet from the wall? So let's look at what we're seeing here, okay? So if we draw this situation, so here's the gym wall. Oh, that's terrible, but you get the idea. You can assume that the ground makes a 90-degree angle with walls and buildings unless you are specifically told otherwise, even if your drawing is terrible. So there is a ladder leaning against the wall, right? So this is a ladder. And again, ignore my terrible, terrible drawings. This is the diagram and rates step, okay? I know that the ladder is a 15-foot ladder. I'm allowed to put that on here because that is always true, right? But the ladder is sliding, so I'm going to go ahead and call this X, the distance from the wall or the base of the gym wall to the base of the ladder, right? And I'm going to call this Y, the distance from this base to the top. As the ladder slides down, right, what's happening is X and Y are going to change, right? The ladder was originally against the wall and it starts to get pulled out by the base. So Pitts is right here, right? And he's pulling the ladder away this way. So what that means is that this measurement would be the rate of change of this thing that we called X, that measurement from the base of the wall to the ladder, with respect to time. And because X is getting longer, it's 2 feet per second in the positive direction. So this is positive because X is getting bigger, right? So it's the rate of change of X, and X is getting longer as Pitts moves the ladder away from the wall, right? This measurement, this thing sliding down here, well, that's going to be dy dt, and what we should expect to see is that that's going to be negative because y is getting smaller as the ladder leans down the wall. So that's my diagram and my rates, right? I then need to take a second and think, what am I being asked to find? So I'm being asked to find the rate at which the top of the ladder is sliding down. That's dy dt at the moment when X is 9, when the base is 9 feet from the wall. So what they want us to find, and it's important to identify that so you do the right problem, they want us to find dy dt at the moment when x, the distance from the base of the wall to the base of the ladder, is 9 feet. Okay, that's what they want us to find. So knowing that, I've got my diagram and my rates. I need an equation that relates all these quantities together. So that equation needs to relate the things I wrote as variables with the thing that happens to be a constant, and that is definitely Pythagorean theorem. So x squared plus y squared equals 15 squared. When I use the next d, which is derive with respect to time, I'm going to get 2x, but I just differentiated some stuff that was not t with respect to t, so 2x dx dt plus 2y dy dt. And then this is the big mistake a lot of people make. That's a 0 because 15 is a constant, and when you differentiate a constant, you get 0. So now I need to substitute in specific stuff to this equation to find the thing I want. I want dy dt, right? That's the thing I want. That was what I was asked to find. So I must know dx dt, x, and y. Well, I kind of do. Now that we're substituting specific stuff, I can look at a different diagram. I can look at a diagram that says that this is 9. I couldn't label x as 9 all the time because remember that this is like a video over here. It's moving. X is changing, y is changing. X isn't always 9, but this is a picture, right? This is a moment when x was 9. Well, you need to figure out what y is, and you can figure that out either by doing Pythagorean theorem or by recognizing that this is a 3, 4, 5 triangle, right? Remember your Pythagorean triples, leg, leg, hypotenuse. One of them is 3, 4, 5. Well, this is 3 times 3, and this is 5 times 3, so this is definitely 4 times 3, right? 3, 4, 5. That's the ratio for this triangle. So you can either use Pythagorean theorem to find this, or you could use the fact that it's a perfect Pythagorean triple that you can figure out. That's fine. Either way, I know y is 12. So when I substitute in, I get 2 times 9 times dx dt, which was 2, plus 2 times 12 times the thing I don't know is 0, right? So that seems to be 36 plus 24 dy dt is 0. Subtract the 36 and divide by 24, and I seem to get that dy dt is a negative 3 over 2 feet. Oh, sorry, dt is what I said. I wrote x, though. Feet per second, right? And I can tell it's feet per second because y is measured in feet and t is measured in seconds. So negative 3.3 over 2, or negative 1.5 feet per second, right? So now I have to answer the question. So let's extend this page down for a sec. So then my last step is answer the question. So the ladder is sliding down, right? Slides down at a rate of 3/2 feet per second, because the word down covers, I can't go down at a negative rate. That would be up, right? So down at this rate. So you found dy dt, but then in the context of this problem, you have to recognize that you were given a direction. The ladder is not sliding down at a negative rate. The ladder is just sliding down. So that covers the 3/2, right? And you could use 1.5, that's fine. Some of you might notice that it could have been easier to solve here for dy dt. So if you had chosen to, back at this step, right, you could have said, hey, I'm going to solve for dy dt first. If you'd done that, you would have gotten that dy dt was a negative 2x dx dt over a 2y. So you would have just gotten its negative x dx dt over y, which would have been a negative 9 times 2 over 12. And you still would have gotten negative 3/2. So if you wanted to, you could have solved for it first and cleaned up stuff. That's fine. Either way, that's my answer. All right, let's go ahead and do P1. So go ahead and give this a try. It is another ladder problem. Try it without me because, again, it's better to get the word problem practice on your own. Cool. Hopefully you tried it without me and now you've unpaused me. So I'm going to do my diagram and my rates. A 25-foot ladder is leaning against a building. So this is the same situation. In fact, I'm going to draw it in the other direction just to prove to you that it really doesn't matter which way you draw it. The only idea is that it matters which way, whether things are sliding in or out. So I've got a building. Hey, look, there's my building. Yay. Okay. And there's a ladder. It is 25 feet long. That ladder is staying 25 feet the whole problem, so I don't have to worry about labeling it, right? So I label my constant. It begins to slide down the wall, so it's sliding this way, at a rate of 3 feet per minute. So I'm going to give this a measurement, right? I could call it y the way I did last time. I could call it h for height. I really don't care, right? I'm going to call it h for height this time, right? So what that's telling me is that dh dt is a negative 3 feet per minute. Why is it negative? Because h is getting shorter, right? As this thing, h is the measurement from the ground up to the top of the ladder. H is getting smaller, so the rate of change is negative. I'm going to call this b for base, right? And I want to know how fast the base is sliding out, so db dt. So the thing I'm asked to find is at the moment when the top of the ladder is 7 feet from the ground, how fast is the base sliding? So I want this, right? I want db dt when h is 7 feet, right? So that's what I want. This is my goal, is to find db dt when h is 7 feet. So now I need to take my diagram and rates, and I need to make an equation that relates them. So again, it's going to be Pythagorean theorem. B squared plus h squared equals 25 squared. You can find 25 squared, but there's not a huge reason because you're going to differentiate. You're going to get 2b db dt plus 2h dh dt equals 0 because a 25 squared is a constant and it's going to differentiate to 0. Now, you know that this is what you want. So again, if you want to solve for it first, you certainly can. You could solve for this. You'd get that 2b db dt equals negative 2h dh dt, and then you could divide by the 2b. So you'd get db dt is when you divide both sides by the 2b, you're going to get a negative h, whatever dh dt is, divided by b. And that's fine, okay? You could solve for it. You could plug in first. It doesn't matter. Either way, when I go to plug in, right, when I go to substitute my specific stuff, I need to look at that moment that they're talking about. Well, the moment they're talking about is when this is a 7 and this is a 25. That's another Pythagorean triple. 7, 24, 25 is a Pythagorean triple. If you don't have it memorized, you can use the Pythagorean theorem to figure it out, right? But leg, hypotenuse, 7, 24, 25 is another Pythagorean triple. The AP very frequently gives you Pythagorean triples in problems. So when I substitute in, I get that db dt, I inadvertently made it capital there, is negative h times negative 3 over a 24, which is going to be 21 over 24, right? I could cancel a 3 from that if I want. I get 7/8 feet per second. So let's go down here and answer the question, right? So my answer is that the ladder slides away from the wall at 7/8 feet per second. Okay. So again, and this is a little bit crammed for space because, you know, apparently I write too big for this, but that's the idea. All right, cool, moving on. A spherical snowball is melting in such a way that its volume is decreasing at a rate of 2 cubic centimeters per minute. At what rate is the radius changing when the radius is 5 centimeters? So when I draw my diagram in rates, it's there's not much to draw on one that's just a sphere. So you've got a snowball, right? I'm trying to give it a 3D feel, right? It's the 3D, and then it's got a radius. That's really all that's happening. So it's melting, so it's getting smaller, right? So when it melts, right, we're talking about the volume changing, and the way you can tell that it's the volume changing is it's 2 cubic centimeters per minute, right? And since it's melting, it's a negative 2 cubic centimeters per minute, right? Because it's getting smaller, right? So what they want us to find is they want us to find the rate at which the radius is changing when the radius is 5. So what they want us to find is dr dt when, that's a t by the way, when r is 5 centimeters. That's what they want, okay? So you need an equation that relates the radius of a sphere to the volume of a sphere. Now, this is one you may or may not have memorized, right? So the volume of a sphere is 4/3 pi r cubed. Now, sometimes the AP does you a solid and gives you that equation. Sometimes they're very nice and say, hey, we get the geometry was a long time ago, we'll do you a solid and give it to you. I would say it's not a bad idea to know basic volume formula type stuff like the sphere, the cone, that kind of thing. And we'll do cone problems in the next video. When I differentiate with respect to time, I'm going to get dv dt. Now notice that the 4/3 pi is just a coefficient, right? So I'm going to get 4 pi r squared dr dt because I differentiated stuff that wasn't t. So I want this. I know this was given right here, right there, and I know r because r was given right here. So that's really my entire job, is to just plug in and solve. So when I substitute in, I don't even have to draw the specific screenshot or that picture moment when it happens. I know that this is a -2, 4 pi, this will be a 25 equals times dr dt, right? So I'm going to get that this is a negative 2 equals 100 pi dr dt. So I get negative 2 over 100 pi, or negative 1 over 50 pi, and it was measured in, so notice that it's dr dt, right? So r is measured in centimeters, and time in this problem was minutes, centimeters per minute. So there's my dr dt, but then I have to answer the question, right? So they ask at what rate is it changing? So my answer is negative 1 over 50 pi centimeters per minute. Now you'll notice here they didn't say, if they had said something like at what rate is the radius shrinking, then I would have not needed the negative, because the word shrinking or decreasing or something like that would have covered the negative. But here they asked the rate at which it's changing, and it is changing at a negative rate because it's getting smaller. All right, cool. Let's go ahead and do another one. So P2, a spherical balloon is being inflated in such a way that its volume is increasing at a rate of 3 cubic centimeters per second. At what rate is the radius changing when the radius is 10 centimeters? So same idea, right? So when we draw, and there's not much to draw with a sphere, like, hey, it's a circle, it's got a radius. There you go. Okay, terrible. Okay. We know that it's getting bigger, right? The balloon is getting bigger. So inflated means gaining air, so dv dt is 3, positive 3, because v is getting bigger, centimeters cubed per second, rather, sorry. We are asked to find the rate at which the radius is changing, which is dr dt, when the radius is 10. So the thing that we want is, that says wand, dr dt, at the moment when r is 10 centimeters. That's the thing we want. So again, as you see more and more of these, you're going to start to realize that the equations are the same, like 4 or 5 equations all the time. The volume of a sphere is 4/3 pi r cubed. In fact, you're going to get to the point where you've probably differentiated this before and gotten dv dt equals 4 pi r squared dr dt, and you think, oh, hey, I've done this before. When we go to plug in, we want this, we know this, and we know this. So when I substitute my specific stuff, I'm going to get 3 equals 4 pi times 100 dr dt. So I'm going to get 3 over 400 pi equals my dr dt, and that should be in centimeters, because r is measured in length units, and here that's centimeters, and seconds for time. So there's my answer, and I can actually just go ahead and put the a there, because that's the answer. That's the rate at which the radius is changing. All right, let's do one more example and one more practice problem, and we'll call it a day for this video. All right, E3, this is a former student shout out. I do love a good former student shout out. Hong Yin and Abdu decided to grab Slurpees from 7-Eleven after AP Calc review. Afterwards, Hong Yin walked north at a rate of 3 feet per second and Abdu walked east at a rate of 4 feet per second. At what rate is the distance between them changing 1 minute after they left 7-Eleven? Okay, cool. So let's draw our 7-Eleven. So when we do our diagram and our rates, okay, let's see. Oh, it helps. You don't have to do this, but I would suggest anytime you have a problem with directions that you do a never eat slimy worms up in the corner, just so you know which direction's which. You can use never eat soggy waffles or sour watermelon, or I don't know, whatever you want, but I always learn never eat slimy worms, and it seems true. I don't really feel like I want to eat slimy worms. So Hong Yin is walking north, right, which is going to be this way, and Abdu is walking east, which is this way. So when I draw my diagram, right, I'm just going to put a 7 there for 7-Eleven. Hong Yin is walking this way, right? Abdu is walking this way, right? Cool. So I'm going to go ahead and use H for Hong Yin and A for Abdu, right? And then the distance between them, I'm going to use D, which is a little iffy because it means you're going to have a dt, but you'll survive, okay? What I can't label on here is the lengths of A and H, because I don't know them yet, right? I know that I can assume north and east make a right angle, right? So when I go to write my equation, yet again, it's Pythagorean theorem, right? H squared plus A squared equals D squared, right? And when I go to differentiate, I'm going to get 2H dH dt, right? Plus 2A dA dt. Oh, I forgot something on my diagram. We'll go back and address it in a sec. Equals 2D dt. What I forgot to label on my diagram, my bad, sometimes my brain is tired, is that we know how fast Abdu's walking and we know how fast Hong Yin's walking. So dH dt, right, dH dt is a positive 3 feet per second. It's positive because H is getting bigger, right? It's not because she's walking up, right? It's positive because the length, the thing I called h is getting larger. Similarly, Abdu is walking at a rate dAdt of 4 feet per second. Again, positive because A is getting longer. It's not because he's walking to the right, okay? So now if you look, I know dHdt and dAdt. I seem to want, they want the rate of change that the distance is, so this is the thing I want. I seem to want dt, which is a lot of d's, at the moment when the time is 1 second. That's what I want, right? This is what I'm asking for. So I seem to know dHdt and dAdt, and I can find h and a and d 1 second after they start walking, because here's the idea. So when I substitute specific stuff, if t is 1 second, that means Hong Yin has been walking for 1 second, which means 1 second in, she's walked 3 feet, and 1 second in, Abdu's walked 4 feet. Because this is a Pythagorean triple, the distance is 5 feet, 3, 4, 5. Now, they're not always going to be Pythagorean triples, right? But I could have used Pythagorean theorem to find that this is a 5 if it wasn't a triple. It did happen to be a triple. So it seems to me that I know h and a and d, and my entire job is to plug in those values and solve. So when I plug in these values, if you want, you could divide the entire equation by 2. If you see that, that's great. So 2 times h times the rate at which she's walking, which is 3, plus 2 times Abdu's position, which is 4, times the rate at which he's walking, equals a 2 times a 5 times the thing I want, which is dt. So over here, I seem to get an 18, right, plus a 32, right? So I think I should get that this is a 50, right, because this is 2 times 9, which is 18, and this is 2 times 16, which is 32, equals 10 dt, right? So I end up getting 5 feet per second is my dt. And that's how fast the distance between them is changing, and that's the answer to the question, right? The thing I called dt, it is changing at a rate of 5 feet per second. All right, last problem, another former student shout out. Kai and Austin gave amazing graduation speeches. Natch. Afterwards, Kai walked south at a rate of 4 feet per second, and Austin walked west at a rate of 5 feet per second. At what rate is the distance between them changing 20 seconds after they left graduation? Okay, so let's draw our diagram and our rates. Remember, it never hurts to do your never eat slimy worms, right? So we know that they are walking, Kai is walking south and Austin is walking west. So when I draw my graduation, which I'm going to put a G for graduation, Kai is going to walk, Austin's going to walk west, so we'll call this A for Austin, right? And we're going to call this K for Kai, right? I know that Kai is walking at a rate of 4 feet per second. Notice it's positive. It doesn't matter that he's walking down. Positive because K is getting longer, right? K is getting longer. The quantity that I labeled K is physically getting bigger. And similarly, dAdt is also positive. It's a positive 5 feet per second, right? And then the distance between them I'm going to call D. You can assume that south and west make a 90-degree angle. So when I write my equation, K squared plus A squared equals D squared, right? The thing I'm asked to find is the rate of change of the distance. So the thing I'm asked to find is dt at the moment when time is 20 seconds. And we're going to talk about what that does to the lengths of the sides in a sec. So at the moment when time is 20. So when I differentiate, I get 2k dk dt plus 2a dA dt equals 2d dt. Now, as you saw in the last one, you might just want to divide everybody by 2 to make your life a little bit easier, right? Like you could, since every single one of these terms has a 2, you could divide by 2. This is the thing I'm trying to find, right? So when I go to substitute my specific stuff in, it matters that the time is 20 seconds because what that means is that Kai, who was walking at 4 feet, 4, not 40, feet per second for 20 seconds, K is now 80, right? And that Austin, who was walking, I think, 5 feet per second for 20 seconds, that's now 100, right? So that's 100 feet. So when I draw my specific diagram for this, right, Austin is 100 feet away from graduation. Kai is 80 feet away from graduation. And unfortunately, this side isn't what you want it to be because it's not a Pythagorean triple, right? So if you think about it this way, 5 and 4, 3, 4, 5 is a Pythagorean triple, but for it to work, 3 and 4 have to be the legs and 5 has to be the hypotenuse, and that's not true here. So when I go to find the distance, there's a couple different ways to do it. Honestly, what is arguably the easier way to do it is to deal with the 4 and the 5 and then recognize that this is just a triangle that is 20 times bigger. But what I'm going to do is I'm going to say, okay, cool, so distance is the square root of 100 squared plus 80 squared, right? So this is a 1 with 4 zeros. This is a 64 with 2 zeros, right? So 16400 inside the root. Great. Okay. So I can definitely take out 100 from that. And I can take out a 4. So I end up with a 20. This is definitely, I can take out a 400 from this. And when I do that, it's 16 and 25 is 41. That seems right. 41. Does that works. So I get 20 root 41, right? So that's the distance. Now, if it were a calculator problem, you could also get that value with the calculator. So once I know that, when I go to substitute in, I would again suggest, if you go back up to this for a sec, I would suggest that you divide everybody by 2 to make your life a lot easier. So it seems to me like my dd dt is equal to k dk dt plus a dA dt all over d, which I can clean up using, so when I substitute this specific stuff, I know all of those values, right? So it seems to me that I can plug in 80 times 4 plus 100 times 5, all divided by a 20 over root 41. This is 320 and 500, which is 820. 820 divided by 20 is a 41. So I end up getting that dd dt is a 41 over root 41. Or if you rationalize, that just comes out to be a root 41. Because if you times by root 41 over root 41, you get the 41s canceling. And that would be in feet per second in this problem. Sorry, couldn't see the thing at the top. So there you have it, right? So at the moment when they left graduation, they're moving at a rate of root 41 feet per second, which if you're trying to figure out how, like, that's the distance between them. If you're trying to figure out how fast that is, you can realize that root 41 is between root 36 and root 49, so it's between a 6 and a 7. So that's our basic intro to related rates. We'll do more related rates in the next video.